Okay, so here I'm picking up on the story of Thomas Kuhn and his account of scientific paradigms, which I covered in another video. So, just to kind of sum up where that last video left off, Thomas Kuhn was very worried about this problem of switching from one paradigm to a new paradigm, his paradigm shift, that it's not clear to him, at least at first, that there's any neutral or paradigm free way to evaluate whether one paradigm is scientifically superior to another paradigm, that there's any way to show that when the scientific community shifts from an older paradigm to a newer paradigm, that there's a way to show that the newer paradigm is scientifically actually better, or that it's closer to a true understanding of the way nature actually is. His term that he used for this was to say that rival scientific paradigms might be incommensurable, that there's no way to really compare them in an objective, neutral way to show that one is scientifically better than another. And so then he was worried further that instead of scientific arguments sort of winning out and the scientific community using those scientific arguments to shift to a new paradigm, instead that they pick a new paradigm or they settle on one paradigm or another, whether it's new or not, for social reasons, that they kind of go along with whatever the most famous scientists are in favor of, or that there's just practical or economic considerations, or even emotional attachments to a particular paradigm that drive their decisions, or political reasons that drive their decisions. These are all non-scientific reasons for picking a paradigm. So then he was worried that if this is the case, that really what science does, at least over the long term, is just sort of jump from paradigm to paradigm. It's not that we can line the paradigms up in a way that shows that the earlier paradigms were further away from the truth and the more recent paradigms are closer to the truth. There's not a way, if paradigms are incommensurable like this, there's not a way to show that science is making progress in the way that we normally think of science as making progress. So this kind of undermines the kind of the superiority of science as a way of uncovering the truth about nature, that instead truth is really just simply relative to a paradigm, and there is no objective sense in which we're getting closer and closer to the truth over time as we sort of improve our paradigms or replace old paradigms with new ones. So this created kind of a large split in academia, or a split that was sort of brewing, but this really kind of exploded things, so that on one side we have sort of the people that are committed to the more common sense notion of science as making progress towards the truth, versus the other camp that believes that truth and understanding, and maybe even reality itself, is determined by sort of social interactions. So that truth really is relative to a paradigm. Truth is relative. There's no objective truth. Thomas Kuhn saw this happening, and in the subsequent edition of his book, he added a chapter at the end to try to clear up some of these things, because he thought that people had kind of taken this a little too far, this relativism of truth, and that somehow science really isn't making any progress. He took it a little further than he was intending. And of course, future people also picked up his themes here and sort of added in for a more robust notion of these theory virtues, as they came to be called. So the theory virtues are what we think a good scientific theory should have. So when we're comparing rival paradigms, they're not sort of radically incommensurable in the sense that there's just absolutely no way to compare them, and in such a way as to show that one is scientifically better than another. It's sort of like in the way that religions are just incommensurable. There's no real objective way to show that one religion is somehow closer to the truth or in some other way religiously better than another religious viewpoint. Instead, Thomas Kuhn and others were identifying these features of scientific theories, that if you have these features, you're a good scientific theory. And if if we have rival scientific theories or rival paradigms, we can use these to compare them to decide which one's better. It could be that one's better in some ways and another one is better in other ways. And really what happens is, as I say here, the theory that has the best balance of all of these is to be preferred. And this isn't necessarily an exhaustive list of theory virtues. There could be others. And as we'll see as we kind of go through these, there's a lot of overlap. They kind of interact with each other in interesting ways. The first one is perhaps the most obvious one, predictive success. So based on a theory, you work through that theory and it will make certain predictions about what should be true about nature or what we will observe in the future. And those predictions can be either right or they can be wrong. And if it's wrong, consistently wrong, then that means that the theory or the paradigm that we're considering maybe is on the wrong track and shouldn't be accepted. Versus a theory that's making a lot of really successful predictions, then that's obviously a good sign that the theory might be on the right track. But it's a little bit more complicated than just saying, do the predictions come true or not? Because there's different kinds of predictions. So for example, there was when Newtonian theory was being questioned and we had these rival theories, rival paradigm, in particular Einstein's general relativity as a rival for Newtonian mechanics and Newtonian theory of gravity. We could say that Einstein's general theory of relativity predicts that if we take an object like this pen and I release it, then the pen should drop towards the ground at approximately 9.8 meters per second squared. That's how fast it should accelerate towards the ground. Okay, so let's test that. It's like, does it go towards the ground? It does indeed. So successful prediction. And if we wanted to be fancy about it, we could measure it more precisely and see that the acceleration really was matching the prediction. It's like, okay, so that's good. It's better than a failed prediction from general relativity, but that's not very impressive, is it? Because we already knew that that was going to happen. We had already measured that, thousands and thousands of times. It was something that Newtonian theory also predicted. So not impressive, right? That's not going to cause us to shift to general relativity because it makes a prediction about something we already know. It's much more interesting if a theory makes a prediction about something unexpected, or even better, something that we initially think is probably wrong, or something that its rival theory thinks will not happen, right? So some kind of unexpected result. So for example, general relativity, in addition to predicting the same sorts of basic things like Newtonian theory predicted, like objects when they're released should fall towards the ground, that sort of basic stuff. He also predicted that the path of light should appear to bend when the light passes through a strong gravitational field, even in empty space. So it's not reflecting, it's not refracting or anything. It's totally empty space, but it goes through a strong gravitational field. The path of that light should appear to bend from people watching it from the outside. Absolutely not predicted according to Newtonian theory. In fact, it sort of contradicts Newtonian theory. According to Newtonian theory, the light should just go straight and that's it when it's traveling through empty space. So this is an interesting prediction from general relativity. And when it was confirmed to actually happen, and not only that, but happen in just the way that general relativity predicted it would happen, now that's impressive, right? That's something that we actually thought, well, the people that were alive at the time in the early 1900s thought should definitely not happen based on their previous theory. So when this new rival theory comes along and makes this prediction that's in contradiction with the previous theory and the prediction comes true, very impressive, right? That's something that can start to sway people to the new theory. So it needs to accurately predict new phenomena, especially really unexpected or surprising things, but it also needs to accommodate things that are already known, things that were not sort of anomalous things that showed up in the old paradigm, like dropping an object in a simple way, like I showed before. Newton made certain predictions about what should happen. There's no reason to doubt that. It's sort of still conforming to modern observations. So general relativity better make the same kinds of predictions. It better be able to accommodate all of those things that we already know. And in fact, it does. It's also helpful, It will sway more scientists to take up work in a new paradigm if it not only generates predictions that turn out to be true, but also practical applications based on those predictions. Is there some kind of new technology or new interesting problems we can solve with this new theory or paradigm that's being suggested? Okay, next, theory virtue. It's sort of a double one that I just squished these together. So it's best when a theory is consistent, that is internally consistent. There's no internal contradictions that could cast doubt on the theory. Also, that it is compatible with other fields of science that already have an established theory or established paradigm. So for example, if some new theory of psychology, I'm just sort of making this up, but let's say that there's somebody's theorizing in psychology that somehow people can transfer thoughts back and forth. Well, we need to have some way that that happens, but further, if they theorize that those thoughts can be transferred back and forth instantaneously or somehow just really fast, faster than the speed of light, well, that contradicts the theory from physics, right? And so unless you can give us a really good reason for thinking that physics is wrong, it's going to cast a lot of doubt on some new theory in psychology that makes a claim like that contradicts a very well-established theory like physics. So it's got to be internally consistent and then compatible with other scientific theories that are already in place. Again, this isn't sort of like this one thing sort of makes or breaks a theory. It's just that this is a reason in favor. This is something to consider when wondering whether some new theory that's being proposed should be accepted or not. Okay, so another thing that every scientific theory needs to have is some kind of causal explanations for the phenomena that that theory is sort of trying to explain. It's got to be causal explanations. So when we want to find out, like, why does something happen? How does it happen that way? Why doesn't it happen some other way? We ideally want to be able to provide microscopic as possible, step-by-step of causal account of exactly why and how that phenomena occurs. We don't want to leave things just as a black box, as we call it. So this is not, when I say black box, we're not talking about like airplane flight recorders. A black box in this context means we know what the inputs are and we know what the outputs are, but we don't really know what's going on inside. We don't really know how we get from the inputs to the outputs. So for example, I'm not a computer scientist, I'm not an electrical engineer, so I have only really the vaguest notion of what actually happens inside my computer. So I treat it like a black box, right? I push a button on the keyboard, something shows up on the screen. What happens in between the key press and the thing showing up on the screen, I really don't know. Electrons flying around somehow, but beyond that, I don't have a causal explanation for how that happens. But if I were to ask a computer scientist or an electrical engineer or somebody like that, they better know, right? They better be able to give me a step-by-step causal explanation for exactly how everything works in a computer. Otherwise, like, how are we supposed to sort of have confidence that we really understand what's going on? So this is something that when people are doing their scientific work over long periods of time, they are trying to generate these kinds of causal explanations. Plus, we can also talk about the scope of the explanations that come from a theory. The more things that a theory can explain, the better. If we have two rival theories that are roughly tied on every other theory virtue and on every other way that we would evaluate these theories, but somehow or another one theory just can explain more things than the other one can, well, then we'll go with the one that can explain more. And by the way, Newton's theory was one of the most unified, had the largest scope of just about any theory that's ever been proposed. And that even counts for today. Newton's theory could explain all of mechanics and astronomy and so on, like all of these things. And so it was all under sort of his unified like laws of motion and his law of gravity. Here's a weird one, at least the term that I use is maybe a little bit weird, fecundity. This is borrowed from population biology, actually. In biology, the term fecundity means sort of the reproductive potential of a species. How many offspring can this species produce under ideal circumstances? That's its fecundity. When used in this context, fecundity means how much research can a theory produce. How much work is there to do for scientists within this theory? How much normal science is going to come out of this theory? And of course, that's a big consideration for any scientists. They need to have something to do. And this kind of links up with the last one, the causal explanations. If we know what the causation is within a theory, how things actually happen, then we can use that to set up new experiments and explore more and more details. So if there's no causal explanations in a theory, then there's not going to be a lot for us to do, right? It's hard to develop new experiments and new research avenues if we don't even know what's actually going on, like what the causation is in a certain field of science. I guess I could bring in here something like astrology as opposed to astronomy, right? In astrology, they make, roughly, they make predictions about people's personality or how their life is going to turn out based on where astronomical objects are in the sky relative to us. Like, okay, but what's the causal explanation? Right? How does the position of things in the heavens cause certain personalities or cause certain things to happen in my life? There is no causal explanation there. So how do I do research on that? How do I test whether this is really working? Astrology is really working as expected. Well, there is no sort of working as expected because there's no internal causal details that are provided. So there's not really much normal science work to actually do there. One other thing, reliable methods. So these are things that tend to be actually preserved, at least somewhat, through paradigm shifts. So there's certain measuring devices, experimental setups, where we have a control group and an experimental group and basis of comparison, statistical analyses, those sorts of things that are sort of tried and true. And so if a new proposed theory is able to take advantage of those things that we know are already really good techniques for investigating nature, then that's great. If some new theory, it might sound really interesting, but we just don't have any measuring devices to test it. Maybe it's a great theory. Maybe in the future it'll turn out to be like pretty much on target, but it's going to be hard to get scientists to accept it because they don't have any familiar methods or technology to use to do their normal science within that theory. So that would be a count against a theory if it doesn't have reliable, understandable methods that we're familiar with. Okay, so one thing that might be glaringly absent if you've thought about this stuff or heard about these things before is simplicity. Sometimes we hear that the simpler explanation is more likely to be true, or scientists tend to go with the simpler theory. So why is that not on the list of theory virtues? Arguably, it could be on the list, but it's a little bit misleading to sort of just throw it out there as just like simplicity is a good feature of a theory. The problem is that nature is not simple. Nature is extremely complex and often very confusing. So we would expect a good theory about nature to also be fairly complex. And in fact, we very often see this as from older theories to newer theories. So, those paradigm shifts that happen that Kuhn was talking about. Very often the new paradigm or the new theory actually is far more complicated and difficult to envision or to work with than the previous theory. Anybody who has learned about Newtonian mechanics and worked with the algebra or maybe even the calculus associated with Newtonian theory, and then tried to work in something like quantum mechanics, the newer theory, the newer paradigm, is a huge leap in complexity. Quantum mechanics is not simpler than Newtonian mechanics. It is far more difficult and far more complicated. So it's misleading, I think, to just put simplicity in there as a thing we want in our theories. However, it can be important when we've got sort of rival theories, and it seems like they're doing pretty much equally well on all the other theory virtues, but one is way more complicated. The mathematics is more difficult, or it's postulating just way more stuff to account for the things that we actually observe in nature. So in some way or another, it's just less simple. Well, that might then be a point against that theory. Like I said, they're both making the same predictions, they're both giving good causal explanations, they're both providing a lot of interesting normal science to do, but one theory is simpler. Scientists are probably going to lean towards the simpler theory. So, simplicity does work its way in here, but it's not something that scientists are really aiming at necessarily. They want the theory to be a good theory in all these other ways. And then if it's also fairly simple, or easy to understand, fine. But if not, oh well, we're just gonna have to deal with it. Using these theory virtues, we can have a way to compare rival paradigms in a way to show that one is just simply scientifically better than another, and to show that science does actually make progress over the long term, that when they shift to a new theory or a new paradigm, that new theory really is scientifically better than the old one, and that there's a good chance that it's actually getting closer to a true understanding or a more accurate understanding of the way nature really is. So, Kuhn then concluded that we don't have that kind of radical incommensurability between rival scientific paradigms that people thought maybe he was claiming in the earlier version of his book. That we can actually sort of translate between theories or translate between paradigms, so that somebody that's sort of, so to speak, living in one paradigm can understand very well what's happening in another paradigm. It's not like it's such a foreign thing that it's like it just doesn't even make sense to them. No, you can understand each other across paradigms and use these theory virtues to come to some kind of a reasoned conclusion to show that one's just scientifically better than another. That doesn't mean that social forces don't play a role. These are humans, so social forces will always play a role. Social connections will always play a role. Psychological prejudices and emotional attachments and all that stuff, economic considerations, maybe even political considerations might play a role. But nevertheless, when it finally comes down to it, when we've got a new theory that's been fully accepted within a scientific community, we do have some ways to show that the new one's actually a little bit better than the old one. Okay, so I'll go ahead and stop there. Thanks.